Hi everyone. Today we are going to start talking about light and how we measure light or capture light using telescopes. So we'll start with learning about wavelength and frequency and how we can use those to describe types of radiation. And we will look at different types of light, how they reach the surface or not. And then we will look at the two main types of telescopes, being reflecting and refracting, compare and contrast, and then also look at the positives and the negatives for using either of those types of telescopes. So before we get to telescopes, we have to think about what are we looking at when we use these telescopes, and what we are observing is light. So light is electromagnetic radiation. It is radiation that comes in from the sun, from the stars, towards the earth. So this electromagnetic radiation has the magnetic and electric fields. It can behave either like a wave or like particles. So visible light, the light that humans can see with our eyes, is any light on the wavelength of between 700 and 400 nanometers. So if we're looking at this wave here of varying wavelengths, the visible light falls right here on this scale between 400 nanometers and 700 nanometers. So all the other types of radiation with wavelengths higher or lower than these values, we cannot see with our eye. So we can only see what we call the visible light. That's why we call it visible light, are the wavelengths that the human eye can see. So when we're talking about waves of light, we talk about wavelength and frequency. So wavelength is the distance between two peaks. So the distance between two peaks in a measure of distance, meters, millimeters, nanometers, that is what we call the wavelength. Now the frequency is the number of peaks that pass by per second. So you can sort of think of it as a speed. It's an inverse relationship with wavelength. So the higher the wavelength, the longer the wavelength, the lower the frequency. The shorter the wavelength, meaning the peaks are close together, the higher the frequency. So this is when we're talking about the motion of the wave. So the motion of this light. Are you seeing multiple peaks very, very quickly, or is there a lot of time in between the two peaks that you see? That would be frequency. So here is a graph of different wavelengths and then different instruments that we use to observe these wavelengths. So you'll notice that right here in the visible, we see the rainbow that we are used to seeing. So that is, these wavelengths here are what we are able to see with our eye. So when we think of electromagnetic radiation, which you might see shortened as EM radiation, light travels at the speed of light, as we call it. It is a constant speed of light. It is 3 times 10 raised to the power of 8 meters per second. And it is always given the letter C. So when you see a little c, it is always talking about the speed of light, which is a number that we know. So if we wanted to find the wavelength of a specific wave, we can do it using these equations. So the wavelength, let me go back and show. So the wavelength here is gamma, and then here we have frequency. I should point that out. Those are always the same characters for these values. So we have our wavelength is equal to the speed of light divided by the frequency of the wave, or the frequency is divided by the speed of is equal to the speed of light divided by the wavelength. So we can use these to calculate the actual wavelength of waves that we're familiar with. So for example, radio. Let's find the actual wavelength of your radio station 98.5. Let's say this is your favorite radio station, so you turn to 98.5 in your car. This is equal to 98.5 megahertz, which is a frequency. So this is actually 98.5 times 10 to the power of 6 cycles per second, which is 1 per second. So we can plug this in and find the wavelength. So we have our wavelength is equal to the speed of light, which is a value that we know, that constant for little c, 3 times 10 to the 8 meters per second, divided by our frequency, which we just found right here. And we find that your favorite radio station, let's assume, is 89.5. The wavelength of that wave is actually 3.35 meters. So these are very easy to calculate once you know either the wavelength or the frequency. So it's very simple with only the 3 values here. But you notice that when, if the frequency were to go up, the wavelength would go down. If the frequency were to go down, the wavelength would go up. So they are an inverse relationship there. So now, thinking about wavelength, we can think about energy. So energy is also inversely proportional to the wavelength. So a smaller wavelength is equal to a higher amount of energy. So this is sort of the same as what we just said. If the wavelength is to go down, the total energy is going to go up, and vice versa. The wavelength is directly proportional to frequency. So if the frequency goes up, the energy goes up. If the energy goes down, the frequency goes down. And one thing to note is the nanometer, which is a unit that you will see a lot when we're talking about EM radiation, electromagnetic radiation. You'll see it as nm. It's 10 to the minus 9 meters. So a lot of wavelengths are reported in nanometers. So I wanted to make sure to say this from the start. So for example, our visible light ranges from 400 to 700 nanometers in wavelength. So that's 400 times 10 to the 9 to 700 times 10 to the 9 meters. So very small. So let's take a look at this graph of wavelengths. So here these values are values of wavelength, and then we see the different types of radiation labeled here as well. And the visual radiation, the visual wavelengths are here, so it's sort of expanded out so that we can see the difference between the range of the visual wavelengths, the way that we're used to seeing it in terms of the rainbow. So which type of rays have the highest total energy? So if you remember, energy is inversely proportional to wavelength. So the highest energy is going to have the shortest wavelength. So the smallest, shortest wavelength would be here, the smallest value of wavelength. So gamma rays have the highest amount of energy. You can also think of that in terms of gamma rays, and X-rays can be quite dangerous. However, radio waves and microwaves, which we use in our house and our cars, is not at all dangerous. So the highest amount of energy are going to be those very, very short wavelengths of the gamma ray and the X-ray. So high wavelength radiation. High wavelength or longer wavelength are radiation that has a wavelength larger than visible light. So generally when we say high wavelength or long wavelength, we are referring to longer than the visible light spectrum. So a larger wavelength than visible light. So these wavelengths will have a lower frequency and less total energy. So this is infrared, microwave, like our actual microwaves in our house, radar that's used for weather, for TV, for phones, and then radio waves, which are used for a lot of communication and radios. So these are harmless to us. They are much lower energy than the wavelengths that we can see in terms of the visual. Now, low wavelength radiation is pretty much the opposite. So low wavelength radiation is going to be very high energy. So it's going to have higher energy than visible light, also higher frequency. So higher energy than visible light is going to be our ultraviolet or UV rays, X-rays, and gamma rays. So these have enough energy to actually be dangerous to humans and other life, harmful to the actual cells in our body. So gamma rays, X-rays, and UV rays can be very, very dangerous. So conveniently, Earth and our atmosphere has made it so that we don't have to deal with those short wavelength radiations. So gamma rays and X-rays are all absorbed in our high atmosphere. So way up at the outskirts of our atmosphere, there's reactions going on that are absorbing and removing all of the gamma rays and X-ray wavelengths before they can get anywhere close to the surface of the Earth. UV rays, so most UV rays are destroyed by our ozone layer, which is in the mid-atmosphere. So it's a thick layer of ozone, and the ozone reacts with the dangerous UV rays, most of them, and destroys them before they get to the surface of the Earth. Now, very large wavelengths and low energy of microwaves and a lot of the IR infrared spectrum are actually absorbed by the water vapor in our lower atmosphere. So these aren't as dangerous, but they are absorbed mostly in our low atmosphere by gaseous water vapor. Now the visible wavelengths, shorter IR wavelengths, so not the whole spectrum, but the shorter side of the IR wavelengths and the radio wavelengths do actually reach Earth's surface. So we do receive visible, shorter IR and radio wavelengths from space, and it will reach all the way to the Earth's surface. The other wavelengths, for the most part, do not make it to the surface of the Earth, which is great because we would not be here if the gamma rays and X-rays made it through our atmosphere to the surface of the Earth. So here is another graphic showing the different types of wavelengths. Here we see the radio wavelengths are reaching the surface, the infrared are not, and the shorter infrared and the visible are reaching the surface, and then we see most of the UV and then the X-ray and the gamma rays do not reach the surface of the Earth. So, now that we know about the types of light, how do we look at them? How do we observe this light out in space? So, astronomers use light to study distant objects. So there's two ways of viewing or collecting this light to study it. One being refracting and one being reflecting. So refracting is another word for bend. So we are able to refract or bend the light coming in using a lens. This ends up with a inverted or upside down image. So what you're looking at will actually be upside down. Now another way is reflecting. So this is, instead of bending, we're going to use a mirror, not a lens, and let the light bounce off of that mirror. So the mirror is always going to be concave in shape, and this will also result in an upside down image or an inverted image. So here I have a diagram that shows what I mean by refracting versus reflecting. So refracting, let's say you're trying to view this object, this candle. So if you are using the refracting technique, you're going to have a lens here, and the lens is going to bend the light that's coming in into a smaller version of the image, but it will be upside down. Now, if you were using the reflecting technique, here you still have the same candle. Here you have your mirror. So instead of a lens, it's a mirror, and it is concave. This shape here is concave. And it will reflect your image into a smaller version, but it will also be upside down. So the way that the light is bent or bounced, it always ends up when what you're looking at is upside down. But these are two ways to observe something from afar. Make it smaller, make it look closer. So something very important is what we call the focal length. So the focal length is the distance from the lens or the mirror to the image that is formed. So the image that is formed being what you see in the end. So the focal length is from, let's say, your eye, if you're looking at this right here, to the lens, or your eye to the mirror. So the reason that the lens and the mirror are curved is you're trying to shorten the distance. So let's say you're trying to look at a star. You want the distance between your lens, which hopefully is within arm's reach on Earth, and the star to be a lot longer than the distance between you and the lens. So by curving the lens or the mirror, you're shortening the focal length between you and that lens. Instead of having the same distance between the lens and yourself and the lens and the object that you're trying to look at. So if we look at these two telescope diagrams, which one is refracting, which one is reflecting? So in this one, the woman is looking through the eyepiece. Here we have a primary lens with light coming in. The lens is bent and then flipped into the image that she sees. In this diagram here, we have the light coming in straight, bounces off this curved primary mirror to this smaller mirror. The light is then sent back down towards her eyepiece. So, if you remember, the diagram with the lens is going to be the refracting telescope. It is bending the light. The diagram with the mirrors is the reflecting telescope. It is reflecting or bouncing the light back into the opposite direction. So both telescopes use an eyepiece. However, the refracting telescope here, A, on the left, it has a primary lens right here, and it has a very long-ish focal point between the lens and the eye. The eyepiece, however, has a very short focal length between you and the eyepiece. The reflecting telescope on the right here, it has a primary mirror, and that's what's used to focus the light into a smaller version. The secondary mirror then just reflects that light back down to your eye through the eyepiece. So the primary mirror is what's focusing the light. However, then it's pointing in the wrong direction, so the secondary mirror just bounces it back down so that you can see it looking into the eyepiece. So here's another diagram. The telescopes don't always look the same. So this is a very similar refracting telescope diagram to what we saw before. But this is another version of a reflecting telescope. So the light comes in, bounces off the primary mirror, is focused onto the secondary mirror. And then instead of the secondary mirror bouncing the light back down, it's actually on an angle. So the eyepiece is on the side of this telescope. So this is a common setup of a reflecting telescope. So let's look at a refracting telescope in a little more detail. So this is refracting. We have the light coming in, bouncing, going through the lens and bending into a smaller version through the eyepiece. So the biggest problem with a refracting telescope is with that bending of wavelengths. So we call it chromatic aberration. And this is the fact that when we bend these wavelengths, we're bending the light that hits this lens. Shorter wavelengths bend more than longer wavelengths. So this results in a separation of the wavelengths or a separation of the colors. So it would be something like this top image. So here we have our light. It's coming in straight at this lens. The lens is bending it. However, the blue light, which is the shorter wavelength, is going to bend more at a more extreme angle than the red. So you end up with this separation. So it's out of focus. The colors aren't going to combine the way that they should correctly because you have this separation in wavelengths that's actually coming to the eyepiece, to your eye. Huge problem. So what we can do is add achromatic lenses. So this would be to add a secondary lens that is specifically designed to bring two wavelengths to the same focus. So bringing two wavelengths together is not perfect, however, because as you can see from this diagram, we added this achromatic lens, which allows the yellow wavelengths to focus into the same position as the red, but it leaves the blue behind. So the blue still isn't perfectly lined up. So these fixes, these lenses are not perfect, and they're very expensive and very difficult. So very tricky to do correctly, incredibly expensive. Reflecting telescopes, however, are much easier, way cheaper, and more sturdy. So we don't have to worry about the difference in bending, because with a reflecting telescope, we aren't bending anything, we're just reflecting, we're just bouncing the light from one mirror to the other. We don't have to worry about the effects of bending the different wavelengths. Another plus is that the telescope only uses one side of your mirror. So with a refracting telescope, you have to have a really perfect lens, both sides. With a reflecting telescope, you need to have a very perfect mirror, but only one side of the mirror. A plus in this is that the mirror can then be reinforced and supported at the back, so it's going to be more sturdy. So it makes these telescopes a lot more stable and less maintenance and significantly cheaper. So if you were to get a telescope to have at your house, you're most likely going to be ordering a reflecting telescope, whether you know it or not. So with telescopes, there's sort of three main components that you're trying to get the best mix of when designing a telescope. You want the telescope to have very high light gathering power, meaning that it can see very faint objects. You want it to have very high resolving power, meaning it has good resolution and it's not blurry. And you want very low interference of the atmosphere. So looking up through our atmosphere, you're looking through a lot of turbulence, so you're going to see blurry images. So let me get into each of these individually and how we can maximize. So the light gathering power. This is essentially you're trying to gather as much light as possible. So you want to be able to see as much light as you can with your telescope. You want to be able to see the faintest of objects. So in order to increase the ability of a telescope to collect light, you can increase the area of that primary lens. So the light gathering power is proportional to the area of the primary lens. So the larger the lens, the larger the light gathering power. Now, resolving power, you also want to maximize. So you want to be able to see really fine details. You don't want to have a blurry image. What is the point of collecting terrific light gathering power if it's going to be all blurry and you're not going to be able to see anything? So there is some unavoidable blurriness due to the characteristics of the waves, the light that you're actually looking at, but you want to try and increase your resolving power as much as you can. So the way to increase the resolving power is to increase the diameter of the telescope itself. So far you want to have a very large primary lens and a very large diameter of your telescope. Now the two main other aspects are the quality of your instrument. So the surfaces must be perfect. So your lens, your mirror, all of the glass pieces must be totally perfect. And then the last piece is to think about the atmosphere. So the blurriness caused by looking through our atmosphere. So if we have a telescope here on Earth and we're trying to view something out in space, that means our telescope and what we are looking at, we are looking all the way out through our atmosphere into space. So what that means is we're actually observing that object behind our atmosphere. Our atmosphere is always moving. So it's going to make your object blurry or wiggle or twinkle. So if you've ever heard twinkle, twinkle, little stars, the reason that our stars twinkle is because we're viewing them through our moving atmosphere. So the atmosphere is moving. It makes all the objects in space appear that they are twinkling, wiggling a little bit, or getting a little blurry, and then a little less blurry, and then a little blurry. So you want to avoid this aspect whenever possible when you're trying to make the most precise observations of objects in space. So if you've ever seen a very large telescope or thought about where they are located, you'll notice that most of the telescopes used for space science are located very high on mountaintops, often away from big cities, but very high on mountaintops. And that's because the air is thinner. You're going to have to look through less atmosphere, so you'll see less of that turbulence. So just trying to limit the amount of atmospheric noise or atmospheric turbulence you have to view through. So by going up on the top of a mountain, you are minimizing how much of the atmosphere you're going to be looking through. So why are telescopes so gigantic? Our most powerful telescopes, now we know, we want them up on a mountain, but we also want a very large diameter of our telescope and a very large primary lens. So this is a picture of the largest telescope. It is 34 feet across. It's a reflecting telescope, and it is huge. Very largest one. So here is another diagram. Here we have our refracting telescope. It is more expensive. It's less compact. We have to worry about chromatic aberration, and it's usually has less light gathering power than a reflecting telescope. The only thing bad with reflecting telescopes is it's made of mirrors, so you won't be able to see any vampires out in space.